and the clock is running differently for it, slightly. And so by doing those things, Einstein was able to predict the proper orbit of Mercury by his idea of space being curved, of space and time being linked. All of this stuff has evidence for it. You didn't just say, oh, hey, great, this is an idea, and everybody loved it. There needed to be experiments done. He'd used that, and then Arthur Eddington, in fact, did an experiment to see if the sun would deflect starlight from behind it, and he showed that it would. How do you see stars when the sun is out? You go during an eclipse. And he saw the shift in the light because, well, as the starlight passes by the sun, unlike Newtonian physics, general relativity should affect it. So it actually shifted the path of the stars, so the stars seem like they moved around the sun. So all of this stuff is there. You just need to crank it up a lot when you get close to a black hole. Yes.
Can you talk about the Spitzer mission in conjunction to what Hubble was in advancement that accomplished?
Well, Spitzer, Hubble, Chandra were all part of what were called the Great Observatories. Each one was to work at a particular wavelength of light. Hubble's main thing was to work from ultraviolet to near infrared. So our eyes work from anywhere between 0.4 microns to about 0.7 microns. Hubble worked from 0.1 microns to about 2 microns. That was Hubble's job. Spitzer works from 3.5 microns to 160 microns. So it's resolution-wise, it's actually not as good as Hubble, but that's because you have to keep it cold. Anything that's warm emits light, and the things that Spitzer was looking for were very cold things. Very cold things emit more in the infrared. Warm things emit in the optical. Really hot things emit in the X-rays. So Chandra X-ray Observatory was looking at really hot things like the gas that's flowing into a black hole. Hubble looks at things that are more like our sun, maybe a little bit hotter, maybe a little bit cooler. Chandra looks at things that are, Spitzer looks at things that are a lot cooler. So it had to be cold. So its mirror couldn't be that big because it's actually, it needed to be cold, and so it gets cooled by liquid helium. The liquid helium ran out last year, so now we have what's called the warm mission. So we went from 5 degrees Kelvin, that's 5 degrees above absolute zero, to a balmy, warm 30 degrees Kelvin. So we can't do some of the science that we used to do, but that's the main thing that Spitzer is doing. The replacement for Hubble, in fact, the James Webb Space Telescope, which should be launched in about 2014, 2015, its wavelength range actually goes from half a micron to about 30 microns. So its overlap is much more with Spitzer than it is with Hubble. Partly because the universe is easier to study there. I was showing you that you can see through dust. Dust is really annoying. And you can, in the infrared, you can see through the dust. In the optical and the ultraviolet, the dust just blocks it. Universe is expanding. Things are being shifted to the red, so they're more in the infrared. So that's really the region that you want to be in for the kinds of science that we're doing right now. The ultraviolet astronomers aren't happy, though.
Okay.
Yes?
Aside from theorizing, what do you think is the most logical attempt to actually figure out what's in a black hole? Would it be possible to send a satellite there one day? Or?
Well, that's the thing. We're always limited by the simple reality that space is big. And I'm not saying this just as a joke. The simple reality is that even the nearest star is 4 light years away. So that is traveling at the speed of light. It takes us 4 years to get there. If the star just somehow magically went out and died, we wouldn't know for another 4 years. And that's the closest star. So the idea, I think, is at the end of this is always to, I'm an observer and I'm partial to experimentation, so that's my bias. And so you want to actually go physically to be able to do this. Either build a telescope that can do that is sitting on the Earth or in orbit around the Earth or near the Earth, but it can detect the emission on a much, right close from these guys. Right now, we don't resolve these sources. All we're getting is the kind of light. We use physics and our understanding to get a sense of what their structure is like. But we've never seen an accretion disk around a black hole. We've never seen an accretion disk around a black hole nearby or far away. All of this is circumstantial evidence. That doesn't mean it's bad evidence. Circumstantial evidence is, the cookie jar is empty, there's a trail of cookies, and then you go to your little brother's room and he's got cookie crumbs on his mouth. Did you see him eat the cookies? No, that's direct evidence. But the circumstantial evidence is pretty good that he ate the cookies. The same here, we have a lot of circumstantial evidence. The emission, the different wavelengths of emission, the variability, how quickly it has to do. It has to be small, it can't be big. If it's variable, it's changing within a day, it can't be 10,000 light years across. So all of this stuff is good evidence, but at the end you really want something that's much closer. So we need to be near it. Then the next thing is, once we're there, hopefully we'll find out enough just so that we'll find out something about inside it. But going inside it is just, that's the problem, is that how do we get information out? Even if we send our own satellite, and if we make it so that it doesn't get split up into and extruded and all that, at the end of the day, I think we need to, once you're there, I think that will give you enough of a clue to possibly figure out what's going on. But it's a long ways off just because, none of these guys are anywhere near us. Sorry, new questions, and then I'll get back to you.
Space is dark. How do you see the black hole in this dark space? I mean,
you wouldn't see it if there wasn't anything flowing into it. That is, pretty much, you need one of two things to be able to notice that there's a black hole there. If it's sort of an empty region of space, there isn't much that will give you a clue. The one thing, if there's no gas, nothing flowing into it, is that it will distort the light of stars from behind it. So basically if one star is here and one star is here, and there's a black hole here in between, from your point of view, these stars would shift closer together. And then if the black hole moved, then these stars would go back to where they were. So basically, it's like a weird lens. So the question is, you can sort of think about it this way, is a clear piece of glass in a dark room is completely unnoticeable. You can't see it. Now, let's say there's a lot of little lights that you turn on, like Christmas lights, and you start moving the lens around. Then you can sort of see it, shifting the light that comes from behind it. And that's what a black hole does. So that's one way of noticing it, is that way it distorts the light that comes from behind it, because it's literally bending the light just like glass bends light for a lens. So that's one way of noticing it. But of course, if there's gas flowing into it, the gas will heat up a lot, so it'll be emitting like crazy, so you wouldn't be able to not notice it. These things become incredibly hot and incredibly luminous. Lots of light will come out from it, even though at the center would be this dark hole. So you see the disk moving in, very bright, but at the center it's a black, just complete blackness.
is this black hole antimatter?
No. Antimatter, that's the thing, is that antimatter and matter annihilate each other. So if there's matter flowing into it and it's antimatter, they should be annihilating and just coming out as energy. So it's not antimatter, or else it would go through a process that antimatter goes through. Whatever is inside it, whatever form the matter has taken inside it, is not behaving like we know of regular matter, even antimatter, as strange as antimatter is. They're different at that. There's something else that's going on. So yeah, antimatter would not behave the same way as we would expect.
My last part of my question. Is a critical mass that some solar object, like sun or something, should reach before it collapses?
Yeah, to start off, if you're going to start off as a star, you have to be about 8 times the mass of the sun and above to end up as a black hole. Because those have a core that will be about 3 solar masses, and that's the limit. That is, when a star explodes, and it's a very strange thing to think about exploding and then leaves a black hole. In fact, what happens is the core basically is just collapsing, but the collapse generates a lot of energy, so it blows off the outer layers of the star. So it loses a lot of mass in the explosion, but the central core collapses. So if the core is about 3 solar masses and above, it'll be a black hole. If it's between 1.5 to 3 solar masses, the neutron degeneracy pressure, it'll collapse, it'll stop. If it's about less than 0.8 to 1.2 solar masses, which is what our sun's core is about, it'll stop at a white dwarf about the size of the Earth. It'll be very strange matter. It's this weird electron degeneracy pressure supported kind of thing, but it will stop. It will not collapse. It will resist the gravity.
Interestingly, is there possible to see formation of the black hole or dying the black hole, or formation and dying?
Well, not so much the dying, but certainly the formation. It's sort of hard to witness the formation itself, but what it is that we know, at least that stars that explode leave remnants. And the question is,